if I know that this is a linear system, and I record this condition and I record this condition, then I can do, without doing the actual experiment, I can predict how the system is going to respond if I'm feeding this input over here. And that makes a huge difference, because that means that with a limited set of stimuli, and actually, and that's too far for this course, but it's quite straightforward what sort of stimuli you should provide in order to be able to know the complete behavior of the system under any circumstance. I can do this. So the good news about linear systems is that they allow me to do predictions without having to do and test each and every condition. There's also bad news about linear systems, and the worst news probably is that, for all practical purposes, linear systems don't exist. Which is bad, right? So take again the example of a neuron that I just gave you. A neuron that fires away action potentials. There is a limit to how many action potentials a neuron can fire per second. I think the theoretical limit is around 1,000 hertz. And this means that if I would keep cranking up the input, keep doubling the input, that at some stage the output will not double, but it will sort of saturate at this 1,000 hertz. Or in the other direction, if obviously a neuron cannot fire with a negative firing rate, it cannot go below 0 with function potentials. So that's a problem. And then for many systems, there's limits to what they can do. But fortunately, there's again an upside. And that is that there are actually many systems out there that are maybe not linear over their whole range. But there is a whole range of inputs where, by approximation, their response is linear. We can consider it linear. And the exceptional cases with the extreme inputs, we can basically ignore that for all practical purposes. And actually, again, in the brain, this is something that happens quite a lot. So let's have a look at a few graphs. And there's things on the axes that we're going to ignore for now. But here we have a graph we have a target amplitude here that ranges from 0 to 30. We have a response which ranges from 0 to 30. And we can see this relation between the size of the target and the size of the response. Does this describe a linear system? Let's see. There's someone on Zoom who cannot see you, so please speak up. Is this a linear system? Yes. Okay, here's another relation. Here we have something on the x-axis, but you can see that on the y-axis there's a sinusoidal relation between the output and the input. Does this describe a linear system?
Not necessarily, but you could, I think, describe it with a large number of linear functions and make approximation.
Yes, but does it describe a linear system? No, it does not describe a linear system. Exactly. Why is this not linear?
It's not a line.
No, that's the wrong answer, actually. Because there's really something different between a line, a linear function, and a linear system. I'll give you an example. And maybe it's on the later slide, and then we can skip it later. You guys remember from high school and maybe later about differentiation. Can you wait for, I was going to answer it. Okay, no, I'll do an impromptu and then you get. Right? You remember differentiation, right? The afterlife. So we have x squared. What's the derivative of x squared? 2x. Very good. Is that something you just remember or something you thoroughly understand?
You sound like you're in the church.
Yes. So what's the derivative of 2 times 2x? Exactly. Yes. So we doubled the input and we also doubled the output. Right? So this means the differentiation, because basically by intimidation in high school, you learned that if you double this, then you need to double that there as well, right? And there's all kinds of good reasons why this is the case, but this is just pointing you out that this is obviously nothing to do with straight lines. It's true for every derivative, but if you, but it's taking a derivative is linear in the sense that we've learned in high school that if you double this, then this will double as well, without a straight line relation anywhere in there. Okay, you were going to answer something, but I forgot what the question was. Yes.
Is linear if the change in y or whatever is on the y-axis is the same regardless of what the level of x is?
Yes. Yes. Basically, what we see over here is that if our x becomes too big, then the rate of change changes, right? And actually it goes down over here. So this is clearly not linear. If I double x, then y does not keep doubling. Can we find a linear range in the sinusoidal function? Is there a range where we can say, well, by approximation, this more or less looks like a linear function? You're nodding yes, right?
Between -50 and 50, we could say that maybe.
Yes.
Because
It says
it's
between
line.
-45 and +45. Okay. Yes, we could say that. Or we could say, well, but it's still going down a little bit, so maybe it's between -10 and -20. So obviously where it's linear is sort of arbitrary. You cannot say here it's by approximation linear and here it's not, because frankly it's not truly linear anywhere. And what you find acceptable is really just what you find acceptable. And has to do with how accurate are the recordings that I can do. How exactly well do I need my model to fit the data, etc. What can I get away with when I'm submitting this to a journal? All that sort of considerations are part of what you're going to say, that you say that this is linear. I think there will be lots of people who will say, well, myself included, if necessary. Anything else so far? Okay, here's another one. Again, another answer to your remark. So here we have another straight line, but here we have the x ranging from 0 to 100 and the y ranging from 100 to 300. Is this a linear system?
Yes.
So if you would do the dirty test, right? So x is 20 and y is, let's say, 140. Now a double x, so we get to 40. So if this would be a linear system, my y would have to go to 280. It doesn't, it only goes to 150. So having an offset, if this line doesn't go through your true origin, through 0, 0, having an offset is killing linearity. You cannot deal with your linear systems anymore. So what do scientists do if they're doing a recording? They usually do a baseline recording that they subtract from everything, so that they end up with just not so much looking at the absolute y values, but the changes in y values, which is a smart trick, because then you get away with the offset. So this is not a linear system, right? But it is a linear relation. Okay, so let's do the same, and now not with graphs, but with formulas, that we see which formulas are linear or not. So does this describe a linear system, this formula? No, because
You have like a constant.
exactly that's what we just talked about, except that the constant is now 3 and not 100. So an offset is bad. This one, is this a linear system? Yes, definitely. Is this a linear system? No, not a linear system. Think of the superposition, right? If we double the input, the output becomes much bigger. And here we have the differentiation that we just talked about, where we've learned if you double the input, if you double the original function, then your output will double as well. Which makes sense because maybe you do remember from high school that differentiation describes the slope of the curve, right? And obviously, if our curve becomes 2 times as big, then all the slopes will become 2 times as big as well. And then obviously, if we do integration, if we do it the other way around, then probably that's going to be linear as well. Okay, this was my very, very brief introduction to systems and linear systems, and now I'm going to apply it to neuroscience and experiments in there. I need to be sure that everyone sort of has a grasp now on what sort of approach we're taking. So what a linear system is, how we're going to move between graphs and super simple formulas. Okay. So my model system is going to be, today is going to be eye movements. Maarten, did you already discuss anything about eye movements?
Yes, in general, yes, yesterday. So we had vestibular reflexes and optokinetic reflexes. Josh also discussed but didn't quite define saccades, like very, he explained what they are and showed
Okay,
the
good. Yep. And everyone completely followed that. It's completely secure about that. I'm very happy.
Can we have a raise of hands? You're completely secure about what VOR is.
I'm not going to talk about VOR, if you know, but I'm going to actually re-explain the saccade, because that's what we're going to do.
It might be in the test.
Oh. Yes. So the funny thing about eye movements is that you make it with your eye. And the reason why they're studied so extensively is first, well, I think there's a bigger underlying reason, and that is obviously that on how you're making your eye movements to a very large extent defines what we see and how we see it, where our eyes are pointing at and being able to keep it at a certain location. And therefore they're crucial for sensory perception, visual perception. The other engineering interesting thing about eye movements is that they are, I guess, the simplest movements that we can make, because the eyeball is one single ball. It can only rotate, right? It has 3 degrees of freedom. It can rotate horizontally, it can rotate vertically, and it can rotate around the pupil. Oh, it's not too bad. If you ever lie next to your significant other in bed and just find a marker on their pupil, and then ask them to sit up, and then you see that the marker is, I don't know, maybe 20, 30 degrees. Sorry?
I was guessing 5. I'm impressed.
Yeah, that's dynamic, but if you're static, then it actually. If you're a fish, if your significant other is then the gain is 100. But if you ever see an aquarium, right? Aquariums are boring except for the eyes of the fish. So if the fish is going down, the eye actually stays upright. So they do that very, very well. So it has 3 degrees of freedom, and therefore it has 3 sets of muscles, basically, that are more or less related to these 3 degrees of freedom. It only rotates, there's no translations involved, there's no joints on top of joints on top of joints. There is, for instance, if I'm doing an arm movement, I can decide to do that carefully or swiftly or abruptly, or there might be an obstacle that I need to avoid, or I need to carry a relatively heavy lift, or maybe I'm carrying nothing. All kinds of things that make arm movements extremely complicated. Eye movements don't have that problem. You're never carrying an extra weight with your eye, except if you're wearing contact lenses. You are never avoiding an obstacle, and it's only rotations. So it's an easy model system to study and therefore easy to understand in engineering terms. This is David Robinson, who did all the good stuff. So that Marianne and I didn't do that anymore. In the end of the 60s. He's an engineer, right? He's really an engineer, a mechanical engineer from MIT, who at some stage, he's maybe first engineer, at least the first that I know of, who really got fascinated about how can I actually use all my engineering knowledge to start understanding concepts of the brain. And the one thing that he, the one very, very reasonable assumption that he made is that the plant, and plant is the American word for factory, right? So that's the muscles and the tissues and everything that physically generates eye movements. The plant of the eye is the so-called low-pass filter. I'm not going to explain exactly the term, but basically what this means is that if I give a rapid input to the eye, it will slowly react to these rapid changes. Actually, many things are low-pass filters, right? If I push a door and there's a spring on there, I can give it a sudden force on that, and nonetheless the door will open slowly. So lots of things that have masses and viscosities and everything will be low-pass filters. Basically, what he was saying is, if I would suddenly yank a muscle, then the eye will have the mass and the friction and everything, so that it will then start rotating relatively slowly. So the eye itself, so the eyeball, the muscles and the tissues connected all together are a sort of low-pass filter. Oh, here's another example. So for instance, the suspension of a car, right, is also a low-pass filter.
If you kick a car, it's also a low-pass filter. If you kick it, and so you get a strong impulse, but it just moves a little.
Yes. And the way these things are traditionally designed, by the way, is by having a spring and a so-called dashpot in parallel. So that's how you make these things mechanically. Now, there's no springs and dashpots in your automotive plant, not unless it works like this. A spring, we all know, right? That's something the more you stretch, the more force it will generate in the opposite direction. So a spring is something that responds to the length of, in our case, the length of a muscle. The more you stretch a muscle, the more force it will generate. Go back. Linearly. Sorry? Linearly. And a dashpot is very much like a syringe, I would say, right? So it's a piston that's moving into a cup, and I don't know how many of you have actually actively, so that's where a class of kinetics comes in handy, have actually pushed a syringe at some stage, but if you do that slowly, then you can actually do that with very little force. But if you try to do that rapidly, then actually you get a lot of resistance and a lot of friction. So where a spring responds to the length of a muscle, the dashpot responds to the rate of contraction of the muscle. If you want to do that rapidly, it will resist a lot. If you do that slowly, it's actually not so problematic. Those two together give you a low-pass filter, responding to both position, length, and velocity. Okay, so Josh told you about saccades. So saccades are rapid eye movements, right? They're rapid eye movements that move the eye from one location to the other. And actually, any voluntary eye movement that we make that's not a reflex responding to either something passing by that you want to follow or something compensating for the movement of your head, any voluntary eye movement that we make is actually a saccade. And there's a bit of a paradox in there. So saccades are really rapid eye movements. We can very quickly, and we do that about 3 times a second, move our eye from one place to the other. On the other hand, I just explained to you that the plant is low pass filter. It's actually not made for making rapid movements. It's made for, well, it's reacting slowly to its inputs, right? So the question is, and that's not the answer to the question now, and that's the question that David Robinson posed himself. So he could see that we were making scans. What sort of input does the brain need to generate in order to make sure that the oculomotor plant can make scaling eye movements?
Yeah, I just wanted to add to you guys, like from a different perspective, what a low pass filter is. Membrane, right? So the cellular membrane, as you're injecting current, is a low pass filter because the voltage changes slowly even if you inject it very fast. Also, if you remember at the beginning of project 1, when we had the Hodgkin and Huxley and the passive membrane, you saw the behavior of a low pass filter. Just wanted to show the generality of the idea.
Yes, because I've been giving 2 mechanical examples, suspensions and oculomotor plant. But again, since you can apply this systems approach to basically anything, electrical properties are an excellent example as well. Then obviously we're not talking about springs and dashpots, but about resistors and condensators. But
Ion channels and membranes.
Ion channels and membranes. There you go. Okay. Oh, yeah.
So the point of the low pass filter is like the speed does not work in like a linear system, right? So the input and output information might like the speed of it just doesn't sound like if you push the button for automatic door really hard, that doesn't have a relationship with the speed at which it works.
Yes, but it is a linear system. I forgot to mention.
It is.
It is, yes. Because if I would push the door twice as hard, the door would actually open twice as fast, right? So again, we're here with the confusion that it's maybe not a linear, like a linear equation relation, but nonetheless, it's a linear system in the sense that if I would double the force to open the door, then actually the door would open twice as fast.
That will be output.
I'll try to sketch that. So if this were my force, right? And then the door would open like this. Actually, this is the best bridge between where we were and where we were going. So this is, thank you for the question. So now I'm doubling my force, right? So I'm now making twice the force, then the door will open like this, where each and every value, obviously this is sketched, where here each and every value is in the red curve is twice as high as the green curve, and here each and every value in the red curve is also twice as high as the green curve. This makes it a linear system. Okay, so we're actually going to use this for a very qualitative approach in the answer to the question, what input does the plant need in order to make the scat? And we're going to use the superposition principle big time now. So what I'll try to do over here is sketch what a scat looks like. So this is the output that we're aiming for. And you can imagine David Robinson with his funny beard and the end of the 60s working on the back of an envelope, working out what's needed for that, right? So here's the saccade. It's a rapid eye movement in space over time. And then obviously by first approximation, you could think, what if the firing rate of the brainstem nuclei that actually project to these oculomotor muscles, what if the firing rate over there would just be a simple step function? So that's actually very similar to what we see over there, right? So it's like generating the force from the door. There's no activity in the brainstem, and then suddenly there is some activity. And then, as we've seen in the sketch on the whiteboard, what you actually expect is that theoretically, if this would happen to the muscles, that this would happen to the eye. The eye would slowly move to a new location. You can see that this is clearly not a saccade, but it is an eye movement, and in the end, it's actually ending on the right position. So now we apply the superposition principle already, because we've basically, this is not a perfect saccade, but there's similarities, right? So the only thing we now need to do is we can figure out what the difference is between those two. So here's the actual saccade, here's the response to a step in activity, and then I've subtracted those two, and then I get this over here. So in other words, if I have this, and I add them together, I end up with a saccade. So now my only next problem is figuring out what sort of input over there would result in this. Because if I can fill in this blank over here, if I know what's going to cause a response like this, then this plus this is this, and therefore this plus this should be the actual input to the plant. Again, we're on the back of an envelope. So what you can say is, well, if I look at the first part, so not what's now covered, but actually if I look at this part and this part, they actually look very similar, but they're skipped, right? This is actually 4 times as steep as this. So this means that, again, with the superposition principle that we're going to use a number of times now after each other, with these 2 parts, this means that the first part of my graph will actually be the same as what we see over here, except that it needs to be 4 times as high. So we're going to have something that goes all the way to here. You see how they are very similar. And the second part, they're actually very similar as well, except that they're moving in the opposite direction. So the thing has to go back again. And in the end, if you think about it, the thing with a low-pass filter that will lead to a response like this is not a step, as we've seen over here, but something that we call a pulse. Not a true mathematical pulse, because that would have time 0, but like a burst of neural activity. So this is neural activity, right? This is spikes in the brainstem that will make the muscles contract. So what we see over here is a step of neural activity that will actually drive the eye to the right position. So this is driving the spring part of our low-pass filter. It's making sure that we get the right position. And here's another bolt of action potentials that are there in order to make sure that the eye actually moves at a high speed. So this is overcoming the resistance of the piston, of the syringe. So we add those 2 together, and so what we now know, without doing any experiment, right, is that if we want to make a saccade, and we know that the plant is a low-pass filter, that then the firing rate in the brainstem that's projecting on these muscles must be something that's like a pulse step. So every time we make a saccade, there's a burst of activity, and after that, there's a higher activity plateauing, keeping there basically to prevent the eye from drifting back to the position, to the center position. And that's obviously useful knowledge, because then once you start tracking up the brain and you want to stick electrodes in the brainstem, and we'll get to that later, you at least know what you're looking for and whether you can find signals like this. You can do predictions on how these things work. So this is a qualitative approach with just a little bit of engineering thinking that already tells us something about types of activities. That's not a question, right? The types of activities that we find in the brainstem. The oculomotor brainstem projecting to the oculomotor muscles. Any questions so far? Who thinks this is really, really complicated? Who thinks this is really too simple? We should speed up a little bit. I now see this as an encouragement to continue the way I'm doing. Right? So, okay, yeah.
Okay, I have a question. I think you explained very well. So
Oh, okay.
I have a question. How did you know that it was like a linear system?
So so he knew, and that was a bit more than just a linear system. He knew it was a low-pass filter. And from engineering, we know that low-pass filters are linear systems, right? And you can say it's almost like an educated guess that something like that would add as a linear system. But it's also something you could, and maybe he did that before, and I don't know about that. You could, with engineering, you can quite easily test that, right? Because this is tissue on more or less on the outside. You can just take a muscle and start pulling it to see how much resistance it has. So that's really tissue property experiments. Okay, let's make this a little bit more of a quantitative approach, which actually requires a bit of experimentation. So one of the next steps that Robinson undertook is actually doing animal experiments. This is my attempt at a monkey. Because he was recording in monkeys, he was recording from the neurons I was just describing in the automotive brainstem that are definitely not that big. That's because it's schematic, right? So you have a monkey, the monkey is awake, the monkey is capable of making eye movements, recording the eye movements. We were still using oscilloscopes at the time. I was 2 years old, Mario wasn't even born yet. There's an electrode going through an axis through the brain, through a pot over here, into the neuron. And what we can do is we can record the activity of the neuron as the monkey is making eye movements. You can do this because paradoxically, you can stick, so these electrodes are basically very sharp needles, right? And paradoxically, the brain is the only organ that we have that cannot sense pain. Whereas all the pain that we sense is being sensed by the brain. But if you stick something in the brain, there's no sensation. So you can do that with an animal who's awake. Obviously, there was an operation before that where you made the axis, and that's painful, and the animal has to recover from that. But once that's going on, you can have awake animals, and without any harm done at the moment during the experiment, you can do these recordings. We also do this during brain surgery nowadays, right? Very often we do brain surgery on people who are awake, so that we can test. Again, we as in we humanities have never done brain surgery, so that we can test their vital functions or functions that they really want to have preserved, such as speech or fine motor capabilities. We can do that because you're actually not feeling it as the surgeon is working on your brain. Okay. So we have the plant, and basically, if we want to, I'm going to skip back a few slides. What we now want, because all of this is qualitative in the sense that we know we need this pulse and we need this step, but we do not know how many action potentials actually need to be generated in the pulse, how many in the step, and what's the ratio between the two. So you start now navigating with your electrode through the brain until you find an area where, as the monkey is making the eye movements, you actually hear the action potentials, which you can play them over your speaker, behave in the way that you predict. There's this burst of activity every time an eye movement is made, and there's this tonic activity whenever the monkey is fixating somewhere in the periphery. And you end up with your electrode in the nucleus abducens, which we now know is actually the part of the brainstem that generates these things. And you hear like this almost beehive sound with the that was my impression.
Notice that it was like, and there's a baseline. No, there was not a.
That was the step I was.
Yeah, exactly. So if they already had some neurons and they had the orientation bars from Hubble and Diesel, and those go like brrr, brrr. So there's no baseline.
Okay, so we do a few experiments, and one experiment that you could do is, and we now can do that systematically, and now we know we can completely characterize that. We want the monkey to simply fixate straight ahead and see what the activity is. And we do that because we want a baseline, right? Because we want to make sure that we're dealing not just with a linear plant, but also with a neuron that we can talk to in linear terms. There may be some baseline activity, as Mario was describing, where the monkey is doing absolutely nothing. It's just staring ahead, and nonetheless there's neural activity over there. And if we want to have our linear systems approach, we need to get rid of this offset. So we just ask the monkey to look straight ahead. We train the monkey to do that, and we record how many action potentials there are actually there. And typically what you would find is about 100 hertz. So that's quite active. Most brainstem neurons are much more active than the neurons that you find in the brain. 100 hertz, 100 spikes per second for doing absolutely nothing. And in our formula later on, we will simply subtract those 100 spikes per second. A spike is an action potential. So we do a second experiment.
Can I just
Yes.
interject for a second? Think about resonators that are spontaneously firing, right? So this is type 2 neurons that have spontaneous baseline levels. Yeah.
So we do a second experiment, and now we want to know, because we want to know the height of this step, right? So the position component in the activity of the abducens neurons. We'll simply ask the monkey not so much to make saccades, but to fixate at different locations. So fixate over here, fixate over there, fixate over there, fixate over there. Have a steady eye, not a moving eye, just a change in position. And while the monkey is steadily fixating these different positions, we will record the activity. And the equation that we then get is measured activity that we have is our baseline activity, which was 100 spikes, right, per second, plus some constant times the eye position. Now we give eye position in degrees. So this is straight ahead. This is 10 degrees, 20 degrees, 30 degrees, etc. And the value of K that you see over here is then about 4 spikes per second, so 4 hertz per degree. In other words, if I'm looking straight ahead, there's 100 hertz. But if I'm looking at 10 degrees off center, not making an eye movement, just fixating 10 degrees, then you get 10 times 4. So then my record is firing rate 140 hertz. Yes.
How did the researchers fixate the monkey gaze?
Yeah, they would train the monkey to do so. But that's why you do this in monkeys, not in rats or whatever. And you can this is something that's quite straightforward to train monkeys. So they're fixating positions, and if they do it then properly, you give them a reward. I think in order to train a task like this will take you maybe 1 or 2 weeks, and then they will fully cooperate. And then every time they're fixating, usually the reward is liquid reward, so they have a little straw, and they get a bit of apple juice, and that keeps them working for several hours a day if they want to. Well, they do not always. And then we need the last part, which is the velocity bit, right? And you can do that in very different ways. What Robinson actually did is he moved away from the static system altogether. He says this plant is being used by all types of eye movements that we have. So we now go to smooth pursuit that I assume you've covered as well. And what we will do is we'll have a monkey that's now with his eyes following a moving target. The target is moving like this. And so and we'll measure the activity every time the target passes through the center. And if it moves slowly, then the eye will have a slow eye velocity. And if it's moving faster, then the eye will have a much higher velocity. And therefore, we can get a very straight relationship between the activity in the abductions and the eye velocity. The EDT is the derivative of eye position, which would be eye velocity. And basically what he found there for the average neuron is that the value of R is about 1 spike per degree. It's 1 spike per second per degree per second. I mentioned this is correct. And so this gives you a relationship between eye velocity and firing rate in the abductions nucleus. Now we need to generalize that, so we want to can combine these experiments. And then we end up with the following formula. The firing rate in the abductions nucleus at any given point in time is this offset, spontaneous activity, plus some constant times the eye position that you have at that moment, plus some other constant times the eye velocity that you have at that moment. Is this a linear equation? No, because there's an offset in there. But if we get rid of the offset over here, right? So we simply subtract that, and our output is not so much the absolute firing rate, but the change in firing rate. So we're going to say differences in firing rate, delta firing rate equals the measured firing rate minus this baseline that I reported in advance. We get the following equation. Change in firing rate is some constant that we've now reported, which was 4 times the eye position in degrees, plus some other constant times the eye velocity in degrees per second. And this is, first of all, a first order differential equation. It's a differential equation because it's an equation that's only made up by a function and its derivative. That makes it a differential equation. And it's first order because it's only the original function and the first derivative, right? Velocity. If there would be an acceleration component in there, it would still be a linear function, but then it would be a second order differential equation. So if you're in bed next to your significant other, you've checked out the thing, you can afterwards brag that you now know what a first order differential equation is. Two things for homework. Yes, so this basically describes therefore how the automotive plant works. How you can put the automotive plant, which is muscles and tissues and the weight of the eyeball, etc., etc. So a complicated biological hard entity. We can actually now replace that by the properties of a very, very straightforward formula and use that for all of our modeling and all of our understanding on how the brain should be functioning. So we've made progress with just a few very simple experiments. Who wants a break? Or do we just move on and finish as quickly as possible? Yeah, move on. Yes? Sorry, I can't hear if you are. So you have to start over again. Yeah. Yeah? Yes, we can do that. So in that case, would K be the spring constant? This is the spring constant, yes. It's not a coincidence that we're using the same K that we would use for spring. Because this is a relation between the input, which in the spring would be force, right? And the length of muscle, which would be the length of the spring. So it's a very similar constant. And here we have the R constant, which is actually how much it's related to the velocity. So this is the dashpot component in the original thing that I had drawn.
A little bit.
Yes. Let's do because maybe some other people, let's do another 7-minute break. Right? Then we have 7 minutes breaks. How are you guys doing on the math? Maybe you're all engineers and this is all ridiculous. Because the next thing is going to be a little bit more mathematical.